So I guessed, and I was wrong. Hello, I'm Kyle. On this episode of Engineering Judgment, we're going to look and see how much bolt torque actually turns into usable preload. Now, a lot of people have already done these tests, and I could look up their results, and I normally do when I'm designing equipment, but I think it's important for me to actually do the tests myself so I can compare my results with what other people have gotten. Sometimes it just really helps me understand the theory more when I actually put it to the test myself. Now, this isn't a super high dollar production, and as you'll see later, some expense was spared in the making of this video. Let's go ahead and just go over the outline so you can see what to expect and the order it will go in. Hopefully we're going to follow it pretty closely, even though I'm going to be winging it through most of the sections. Do you really think I have time to script all of this beforehand? Throw hands into the air in disbelief. Next page. So we'll start with a very brief overview of what bolt preload actually is, why it's useful and important to us. Then I'll go ahead and sketch out the basic idea of the test, what everything's going to look like as far as the actual members and fixtures go. We'll do some calculations so that way we know what to expect before we do it and how far the bolt length is expected to change when we torque it. After that, we'll actually have to build some stuff so we can do the test, so we'll go through all those steps. Then we will do the actual testing and get the results. I have them shown as two things here, but we may combine them into one section. We'll see how that goes. And then lastly, we will just go over conclusions of what we found, how it compares, and any final thoughts. So what is preload exactly? Well, preload is the tension force that's created when you tighten a bolt. So if we were to tighten this nut here, it would generate a tension in the bolt that would then compress the members around it. These arrows approximate how much of the members are actually compressed when we tighten it. There are a few methods to do this, but we're going to use the hollow cone Frusta method like Shigley's does for our work. Preload is one of the most important parts of creating a bolted joint that actually works correctly. Again, that's because it is what actually puts the members into compression. Here's a slightly better shaded view of that area. The stiffness constant of the joint, C, is commonly less than 20%. This is actually the percentage of the external loads. So if we have the total force of the bolt, that's going to be this right here, which is our stiffness constant of the joint, which is 20%, times the total external load here, plus the total preload that we actually put into the bolt. This works because everything basically acts like a spring. The bolts are elastic. I'm not really going to get into how this works here. You'll just have to take my word for it, but just know that the stiffness constant is the bolt over the bolt plus the members. And so that is how the bolt ends up carrying 20%, and the members, or the energy that's stored in them, carries over 80% of any external loads. So how do you measure preload? Well, the most common way, and you're probably aware of it, is the torque wrench. You use it to set the amount of torque that either is applied to the nut or the head of the bolt. It's not super accurate at about plus or minus 25%. You might be wondering why we use it when most of the other methods are more accurate, and that's because it's easy, cheap, and most of the time it's good enough. Another great way to measure this is with bolt elongation. That actually checks how much the bolt stretches under a known load. You can see here that bolt elongation is plus or minus 5%, which is way better, but it's much more difficult to actually measure. So here's a slightly closer look at bolt stretch, since that's what we're going to be using today to check how much of our torque actually turns into preload. The formula here is deflection is equal to the preload times the length of the bolt that's actually in the grip, which is like in this area, all over the area times Young's modulus. So it's not a very difficult calculation to get the deflection. It's just generally hard to measure because, as you can see here, it is impossible if you can't get to the end of the bolt, or if it's too far from the edge where you can't reach it with micrometers. That's why a lot of the times you can't actually do this, even though it is much better. As we saw, there were much better methods like ultrasonic sensing and strain gauges with plus or minus 1% accuracy, but I don't have the stuff for those. So we'll just have to settle for bolt stretch. So that being said, even though sometimes it's impossible, I'm going to specifically design as a fixture so we can apply a known torque and then actually get to both ends of the bolt. So that way we can accurately compare what we think we're going to get versus what we actually end up getting. So let's get a quick idea of what our test fixture is going to look like. Now I have some steel flat bar that I've had laying around for a while, so this seems like a good use for it. As we mentioned, this does need to be designed so I can get to both ends of the bolt so we can actually measure how far they stretch. So we'll probably end up chopping this bar into a few pieces so that way we have a decent grip length, and we'll go ahead and do something like this, and we'll carry this down. Now I do want a row of bolts because in addition to checking how much preload is created when we torque the nuts, I want to see how much they crosstalk. And what I mean by that is when you torque these bolts, let's say you torque this to 50 inch-pounds, and then you move and torque number 2 to 50 inch-pounds, it will actually squeeze the members and it will lessen the preload in number 1. So as I go through here, I'm going to take multiple checks of the length as we torque these in a row, and maybe we'll actually be able to detect that crosstalk. Now, this is our basic member layout, and I'm going to have to hold this somehow, so I'm thinking about putting a U-shaped board that I can lay this piece across. So we'll have our bolts going across here. We can bolt this down. We will C-clamp this to the edge of the workbench right about there. I think that's pretty much it. I am going to do 10 bolts. That's a nice round number, and that's all the material I have. So that's how we're going to handle it. It's going to end up looking something like this. We're going to make sure that the nut is on top with a washer underneath, so that way it will be easy to torque. I am going to end up using quarter 20 hardware like this, so that way I can easily bring them to the right torque for the preload, because if I were to use something like 1.25" hardware, my arms would get pretty tired. Now that we have an idea of what our test fixture is going to look like, let's go ahead and do some calculations to figure out what the torque should be and how far we think the bolt's going to stretch before we actually find out in the test. So let's run through some quick math here. Nothing too bad, I promise. One quick note is all of this assumes that I got grade 5 bolts. I ran to my local hardware store and picked some quarter 20s out of the grade 5 bin. Apparently I wasn't paying too much attention, and now that I'm looking at them, they don't actually have those 3 lines that indicate that they are grade 5. They actually have text on them that has YC something or another on them. So these might actually be a lower grade of bolt, may even be 1 or 2. Let's see if we can figure that out. I have the specs here for the different grade strengths, and as you can see, we're going to actually be shooting for 85 KSI as our proof strength if we were using grade 5 bolts. Our torque wrenches are roughly 25 plus or minus % accurate, so that'll mean we'll end up somewhere between like 64 and 106 KSI roughly when we actually go to tightening these. So as you can see, we will actually be exceeding the yield strength of grades 1 and 2, and more than likely we'll be exceeding the tensile strength, definitely of grade 1 and maybe even of grade 2, depending on where in this range we fall. So I believe it'll be fairly easy to tell if we ended up with grade 1 or 2 bolts, because they'll either permanently deform because we've pulled them into the plastic range, or they'll just completely fail. So I think we'll be able to tell. We'll do a quick check before we actually start running the test to make sure that I have the right hardware. Now, assuming we actually have grade 5 bolts, you can see that the preload force here will be 2,000 pounds. Seems like quite a lot for a quarter 20, doesn't it? I'm going to be shooting for 75% of the proof strength here, so that way I can reuse the bolts because I plan on torquing them several times. If you weren't, you could run this closer to 90%, but I've gone ahead and chose 75 for this test, 2,000 pounds. Here's the required torque for the 0.2, which is the dry zinc bolt torque coefficient, times the preload we're going for, and then the nominal diameter of our bolt, which is 1/4 inch. So we have 101 inch-pounds as our initial torque that we're going to be running through. We're going to be doing zinc plated dry bolts first, so we'll use 0.2, see what that does. I plan on doing 2 or 3. I'm definitely going to do zinc plated and lubricated to see if we can detect that difference. I have a suspicion that not only more torque will be turned into preload with the lubricated bolts, but the scatter between the points will be much less when it's lubricated. We should be able to detect that with some fun statistics when we're done on our results. If I can, and I plan on it, but no promises, I'm going to do a Molly test as well because it is much lower on the torque coefficient. I've gone ahead and mapped out those 3 torques here for the dry condition up here, just some plain oil that I have lying around, and then some actual Molly lube. And you'll notice that this is actually half, which is pretty incredible, showing how much difference that better lubrication can actually make when it goes to getting the correct preload that you're after. So now that we know the torque, we can, or technically now that we know the preload force, we can figure out how much we expect these bolts to stretch. You can see our formula right here. Delta is equal to the preload times the grip length over AE, which is the area times Young's modulus. We get 7/10 of a thousandths. Yeah, 7/10 of a thousandths expected elongation. Not very much, but we should be able to detect it. So this is what we expect to see, and it should go back to the original length if we have the correct hardware. If we show some sort of permanent set or completely snap, this is how we'll know that we have inferior grade bolts. And I wasted 16 whole cents on these hardwares. This same formula right here, we're going to rearrange to be able to verify how much preload actually gets into the bolts. So if we take this and we solve for the preload, it will be the deflection times area times Young's modulus over the grip length. And now this right here is what I'm going to be recording during our tests, and then I'll be able to throw this into a nice spreadsheet and calculate the preloads for every bolt after every pass. I think that's about it. Math wasn't too bad since we don't have to worry about how well this joint is going to work. We just have to worry about what preload we're ending up with. So now that we know what to expect, let's head over to the workbench and get started. So I just got back from the hardware store picking up everything we're going to need for the test. And now I know this doesn't make sense at first, and that's because these are actually legumes. Holy crap! So now I've gone ahead and punched the rest of these holes. And as always, after you use your impact punch, it's very important to remember to go back and deburr your holes. If you don't deburr your holes, I'm going to find you. And so now it's time to go ahead and cut this to length. Now that the holes are done, I'm going to make 3 of these because that's how much material I have. So let's go ahead and get our string line out. It's very important that you get the straight one because you don't want curved cuts. Let's go ahead and get this done here. Oh, there we go. And as you're all aware, benefits of the string light include already smooth edges. No need to file. So I'm going to go ahead and get this ready, recharge it for the next cut, and I'll be back after I finish making all 3 of these. I have left enough space at the end to do the mounting holes, but we will sort that out once we get the fixture made to hold these members. So now we have our 3 parts here. Let's go ahead and do a quick test fit, make sure everything went well. Wait a minute. Some of these holes don't line up. Who made this? To whom it's about to concern. These parts don't fit, and you should be ashamed that they left your shop. You are clearly certified to ISO 2015 instead of 2008. Send.
You've got mail.
Well, it looks like that email did the trick. Got that sorted out. Turns out that the punch he was using was not in calibration, so sent that out to be recertified, and what do you know, now everything lines up. Even got the mounting holes thrown in for free to make up for the poor job the first time. These are going to hold this member set here in our fixturing when we go to do all of our testing, and we're going to be making that next. It's times like this where I remember how soothing it can be to watch a master at work. We have everything bolted into our fixture here, and as you can see, we should have enough room to get a wrench on the bottom and then put our torque wrench on the top. The next problem we're going to run into is the top of these bolts are not very flat, so it's not going to make a very good place to use my super accurate precision high dollar no name micrometers on. So what we're going to do is we're going to end up stacking 2 of these nuts just so that way I have a reference, and then I'm going to file the ends of these down flat, and that should be good enough for what we're doing here. There we go. That ought to do it. 1 down, 9 to go. Also smoothing out the tops. That should be good enough. Now we'll be able to, more accurately measure the length of them with the micrometers, since it'll be able to sit square. Here you can see it mounted in the micrometer. It's actually pretty good. Can't see any light going through it on either side. I would show you with the flashlight, but unfortunately I don't have 3 hands, so you're just going to have to take my word for it. But we'll do this to all the bolts so I can get accurate before and after length measurements, and then we'll get testing. So before we get started measuring our bolts, let's verify our tools. Only the finest metrology equipment here, and I can prove it because I have the certs. We got our standard here, so let's go ahead and check it. 0.7345. Only the finest metrology equipment here, and I can prove it. Here's our standard, so let's go ahead and check it. 0.7345. Perfect. Okay, so I'm actually only looking for the difference in measurements with this test, not the real measurement magnitude. So as long as these measure the same wrong every time, they'll be right enough for me right now. I mean, could I have bought better micrometers? Yes, I could have. Did I buy better micrometers? No, I did not. Instead, I used the mic money that I could have used for a better set of Mitutoyo micrometers on a better Rode microphone. So, using this mic right here, you'll be able to hear how wrong this mic is in stunning 32-bit auditory clarity in the workbench segments. And besides, the included lav mic cord is multi-purpose. Forgot the socket. There we go. And it's even the right size. Okay. We're going to start by verifying that our bolts are grade 5 and not 1 or 2. I've already measured the length of all of these and put them down over here on the tablet. This first one is 0.8684. They are just barely snugged, just enough that they don't turn. We're going to go ahead and bring them to 102 inch-pounds, and then we'll see if it takes a permanent set. So let's go ahead and set this. 102. Well, this goes in even increments, so that's as close as we'll get. It also is close enough. So let's go ahead and torque this first one to 102 inch-pounds. Now let's use the longer wrench, just so it's slightly easier. This isn't a bunch of torque, but it's just easier to hold on to. Okay, I went ahead and clicked it twice. It's not a super snappy torque wrench, but it did trigger. So what we'll do is, now this is at 102 inch-pounds. So I'm going to take the length measurements now, and we will see how much it has stretched. Okay, so just to avoid addition mistakes, I brought a calculator. So we're at 0.8691, and then we'll subtract our starting length of 0.8684 for 7/10. And we were shooting for, what was it, 6.8, so this is basically right on. I'm going to go ahead and mark this down here, because now we're actually starting to record data. So now this is 8691. There we go. And so now what I will do is I will loosen this off and check the length, because what we're trying to do is make sure that it has not permanently deformed. Okay, so this is now loose. I'm just going to barely snug it by hand so it's not turning. Now we will check our length. We have 0.8683 technically, and our target was 8684. That 10th difference is more than likely just due to the accuracy of this micrometer. So what we have learned is these are not permanently deforming. So they're either grade 5 or close enough as that grade 4 that we saw in the chart, that they're not taking a permanent set, at least not this one. I'll verify this after we do all the tests to make sure none of them have taken a permanent set, but I believe that we'll be good enough to continue, which is nice because I've already filed all these and I didn't particularly want to do it again. But I did buy actual grade 5 hardware where you can see the 3 marks on top, that we can redo this, and I may redo a couple of them anyway, just to see how those behave in relation to these. So now that we have that, I will go through and torque all of these and record the measurements so we can figure out our first test with the dry zinc bolts. Here goes nothing. Well, the good news is, after I retorqued it, I got the exact same measurement, 0.8691, as I did the first time, so that's nice. I'll now continue on, and I will check for crosstalk. And so after I do number 1 here, because I have them labeled 0 through 9, after I do number 1, I'll go back and measure 0 here and see how much it is decreased, because as these subsequent bolts clamp down on the members, it will actually reduce the preload in the bolts that we've already tightened, which is why you do multi-passes and you go in specific patterns. Now we should be starting from the center and going out, but for this test, I'm just going to go in order, and we should be able to see the results of that. So, continuing on. Now let's go back and measure bolt 0 and see what we've changed, if any. Okay, so after its initial torquing, bolt 0 was 0.8691, and now it's 0.8687. So it has decreased. So I'll go ahead and write that down. So that's 4/10. So that's almost half of what stretch we got. So that's actually pretty significant. I will now continue on. I'm not going to go back and retorque them until I'm completely done. Now on to bolt number 2. I'm now just beginning to realize just how long this test is going to take. I hit clear. Excellent job. So why do I keep measuring the ones to the left of the ones that still aren't changing preload? Because I don't expect them to change. Well, I take measurements even when I think I know the answer, because otherwise there's no point in actually doing the test if you skip the obvious steps to you, because then you won't ever come across anything that's unexpected. Syntax error. Okay. Rate 5 still. I'm getting a weird reading here that's much different than I'm expecting, so I'm going back to double check. I'm showing a slight loss of preload now, which is interesting, more distinct than in previous passes. That one did not have a loss in preload. So I've made it through all of the first test, torqued all of them, and then went back and checked each previous one after every time. This was, again, just the dry zinc plate to 102 inch-pounds. There was one interesting result. We will take a look at those, but number 6 here actually lost most of its preload when number 7 was tightened. So we'll take a look at that in the numbers, and then I'll also go back and try and see if there's anything interesting about the members right here that would cause that outlier result, because most of the others held their preload pretty well, but number 6 did lose basically all of its preload when number 7 was tightened. So now I'm going to move on to the oil test, and then we'll do the moly test. Setting up the torque wrench for the ARP Ultra Lube test, it only takes 50 inch-pounds, and that is the lowest this torque wrench goes to. Now generally it's better to only use your torque wrenches between 20 and 80% of its range for the best accuracy, but it's far too late for me to go back and start over with larger bolts to stay in the good range. So we're just going to see what happens. Oh wow, that barely feels like I'm doing anything after the first 2 tests. That's considerably less torque. I mean, it is half. It's the exact, actually even slightly more preload than the oil test at half the torque. Hey, what do you know? The math worked. After many clicks, I'm back with the results. We've got the dry shown here with the 0.2 coefficient of friction. Quickly, you will note that there are some columns that are much lower than expected, like number 2, 5, and 6. After inspecting the members, I believe that this is because the bolts were contacting the side of the holes, and so they weren't actually developing the amount of preload they should have. I went ahead and left the results in this test just because I took them, and I just figured I'd leave them in. They might skew our results a little bit, but you know, these things happen, and I figured whatever. So we'll move to the oil results here. This, I assumed a K of 0.18. You can see again that those problem columns were still being an issue. And at the end of this one, I retorqued to 90 inch-pounds. And just to compare with what I had gotten, nothing changed. So I didn't do that on any of the following tests. For our last test, I got the ARP Ultra Torque. I assumed a K value of 0.10. Notice the question mark. It's because I couldn't find what the torque coefficient actually was for this. So I guessed, and I was wrong, as you'll see in a minute. Here are these results. No, we only had to go to 50 inch-pounds instead of the 90 and the 102 because of the much lower coefficient of friction. Let's jump over to the actual results here. We got the dry results here, the oil, and then our ARP Ultra Torque on the far right. You can see that the average of each of these is plotted here. We have the actual target preload that we were going after, the 2,027 pounds. You can see the standard deviations of the dry was 600 pounds off, 458 pounds for the oil, and 388 pounds for the ARP. I believe that these values are off, like the means, because I assumed the friction factor incorrectly. So I could calculate the friction factors and go back and redo the tests. But I don't want to do that. So instead, I've cooked the books, but just a little bit. What I did was this offset here, I added those back in to the results to just kind of make the mean along the actual target. And then you can see the scatter, decrease as you go from the dry condition to the oil to the ARP torque. This is what I expected to see as far as the scatter getting less and less, because you have a pretty wide scatter here for the dry condition, and then as you make your way through the oil to the ARP, it's a pretty close end result to what you are actually shooting for. And again, some of these low values are because of poor test fixture building, so those actually probably shouldn't have been included. So, you can actually just look at these values right here. Would probably be a better indication. I also ran into, we'll jump back over to the results page here. I ran into the limits of my cheap micrometers. It was really hard to get them to read within, a tenth. I probably should have just gone ahead and bought better Minotoyo micrometers, but I did not. So I would like eventually to rerun this test with better equipment and, an actual machined test fixture instead of one with punched holes. I just think that would be a lot more definitive in the answers I'm pulling here. But even with all of these inconsistencies, you might say, I still can see in the data the improvement you get from going from the dry condition to the oil to like a moly base lube or the ARP Ultra Torque. So I am glad that I did this. It took way longer than expected. And, I guess if I really, really cared, we could figure out what the torque should have been for the ARP. I know my average preload that I got when I ran my statistics, and I know the torque that I put in. So using our formula, torque is equal to the torque coefficient times the preload times the nominal diameter. We actually really don't need this because we're measuring the deflection. You can put that in here, and you get K is 0.17. So putting that back into our first formula, instead of 50 inch-pounds, I should have put 86. And this probably would have moved our mean right here much, much closer to the target and been a more accurate representation, because I did just guess on the torque coefficient, and I was wrong. It was actually much closer to the oil than I expected it to be, but even so, the standard deviation, the scatter between the points, was still less. So let me know what you think of these results of this test, and thanks for watching. I'll see you next time.